One of the main uses of capacitors is to store energy. Let's think about gravity for a minute. If I have a motor that can do work on a mass by lifting it up in a gravitational field, I'm doing work on the system, increasing the system's potential energy. I can disconnect my motor and leave the mass at this higher position, and there's extra potential energy stored in the system. And then at some later time, I can release the mass and it'll gain kinetic energy, and I can maybe harvest that and do work on something, get some of that energy back out of the system. The same is true with a capacitor. Here I have a parallel plate capacitor, and I'm going to hook it up to a battery. The battery is going to move electrons around from one plate to the other. This side will end up with excess positive charge, or it will be missing some electrons. And the other plate will end up with excess negatives. And so we've done work on those charges, separating them, moving them from one plate to the other. And there's stored potential energy in the system. We can disconnect the battery, and with the battery disconnected, there's just energy stored in the capacitor because of the charge separation that we created. Now we can hook something up to this capacitor. Maybe we hook up a light bulb. So I started on the left-hand side with a parallel plate capacitor hooked up to a battery. The battery did work, moving charges from one plate to the other. I've disconnected the battery. That's what the center image is on my screen. And it's just storing. The capacitor is just storing charge and energy and waiting for us to try to get that energy back out. And then on the right-hand side, I'm showing what would happen if we hooked up something like a light bulb to our capacitor. Those electrons all repel each other, and they're trying to get as far apart from each other as they can. And as soon as we give them a path to go to the other side where they're attracted to those positives, they will take it. So the electrons will start to flow this direction and go to the other side. And those electrons flowing through the light bulb give it some energy, cause it to light up, and we'll get that energy out of the light bulb. We're going to start drawing a lot of circuits, so we need to understand what symbols we use so we can represent all of our electrical devices in our drawings. A DC power supply or battery can be represented with one of these drawings. The long line on the left side indicates the higher potential side of the power supply or battery, the positive terminal. You can draw it either way. I'll try to draw it like the top one because the bottom one starts to look a lot like the symbol for a capacitor. What is the symbol for a capacitor? Well, most capacitors are parallel plate capacitors. So our symbol is two parallel lines, like a parallel plate capacitor. We also have resistors in our circuit. We'll learn more about resistors soon, but this is the symbol for it, and that's how we would represent it in our circuit drawings. Quite often in our circuits, we have more than one capacitor. So it's important to understand how to deal with combinations of capacitors. Two common ways to hook up electrical devices is what's called series and parallel. Capacitors in series would look something like this. You can see these three capacitors, C1, C2, and C3, are all hooked up in a line together. This is called a series circuit. An analogy I like for circuits is they're like hiking trails. And if you were on this hiking trail, you wouldn't have any choice. As you hiked around the trail, if you went through the first capacitor, you'd have to go through the second one and then the third one. That's how you know they're in series. There's no choice. There's no fork in the road where you can take a different path and bypass one of these. Another common way to hook up circuit elements is what's called parallel circuits. Here I have 3 capacitors hooked up in parallel. You can see that if you were hiking along this hiking trail, you would have parallel paths to get to the other side. As you come around from the battery, there's a fork in the road. You can take a path through C3 to get to the other side, or you can take a path through C2 to get to the other side, or you can take a path through C1. These are parallel paths from point A to point B in the circuit. In order to analyze circuits that have multiple capacitors, we need to understand there are some rules as to how capacitors behave when they're hooked up in series or in parallel. Let's start with series circuits. If our capacitors are hooked up in series, like I'm showing here, we know the charge on every capacitor has to be the same. The charge on capacitor C1 equals the charge on capacitor C2 equals the charge on capacitor C3. So the charge on each of these capacitors is going to be the same, even if these capacitors have different values for their capacitance. And the charge on each capacitor is equal to the total charge in the system. You might say to yourself, wait a minute, I've got 3 capacitors here. Each one has a charge Q. How could the whole system only have a charge Q available? Well, let's think about what's happening. As this battery moves charges around, let's say the battery moves a charge from the left plate of C1 through the battery to the right plate of C3. It's moved an electron, so we end up with a positive charge here, and an electron gets moved around and deposited on the plate over there at C3. A capacitor is an open circuit. There's no electrical connection between those plates. If there was, we wouldn't be able to move charges over and have them stay. They'd run right back to the other plate if there was an electrical connection between the plates. It's an open circuit, no electrical connection. So the charges that move through the battery are the ones that we're doing work on, and they're the ones that we're going to get out in the end. Once one electron is moved around, what happens over there at C3? That electron repels an electron from the opposite plate, and that electron moves. So an electron moves and leaves a positive behind because it's repelled by the electron on the right plate of C3. And over here at C1, that positive charge attracts an electron, leaving a positive behind. So internally, I'm going to use green. Internally here, those charges just redistribute based on what the battery is doing. You can see that if we took this circuit, after we charge it all up, you can see why all the capacitors have the same charge now. And if we charged it up to a certain amount, remove the battery, and put a light bulb in its place, well, how much charge would go through the light bulb? Only this. Only the charges that are on the very outside would go through the battery, and all the ones in between in that green box would just go back, redistribute back to where they came from and not go through the light bulb. That's how you know you don't have that excess charge. So even though there are 3 capacitors in this circuit, and each one stores a charge of Q, there's really only 1 Q available to us. If we were to hook it up to a flashlight or something else, there's only 1 Q available to us that we could get back out of it. The other thing that's convenient is to be able to combine these capacitors and think of them as a single capacitor. What 1 capacitor would I have to use to act the same as these 3 in series? We call that the equivalent capacitance. And for capacitors in series, the equivalent capacitance is determined with this formula. Of course, I drew my circuit with 3 capacitors, but it could have any number of them. If there were 4 or 5 or 6, you would just continue this formula for 4 or 5 or 6 capacitors, whatever you need. You may be wondering where this equation for C equivalent comes from. Well, let's do it for a simple circuit with just 2 capacitors. We know the charge on each of these capacitors has to be the same. We also know that Q is equal to CV for a capacitor. So that means for capacitor 1, the charge on that capacitor has to equal its capacitance times the potential difference across that capacitor. The same is true for Q2. And we know that the potential difference across the first capacitor plus the potential difference across the second capacitor has to equal the potential difference across the battery. That's what's supplying the potential difference, and it's split between the 2 capacitors. Now I can just go back to some of these equations I wrote earlier and substitute in. The delta V for capacitor 1 is just its charge divided by its capacitance. Same for the potential difference across capacitor 2. I also know that Q1 and Q2 are the same. I'm just going to call it lowercase q here. And I want to get this equation into the form Q equals CV. Q is equal to 1 over Q equals CV is our equation. Let's just write it in here. This is the total charge. This is the equivalent capacitance. And that's how you derive it. Now let's look at the rules for capacitors in parallel. The first thing is that the potential difference across each capacitor in parallel is the same. And the equivalent capacitance is just the sum of the individual capacitances for these capacitors. C equivalent is C1 plus C2 plus C3, etc. I can imagine that fairly easily. I have a capacitor C1, I have a plate area here, and I hook up another capacitor in parallel to it. So basically I'm adding this plate area from capacitor 2 to that plate area from capacitor 1. And what does that do? It just makes a bigger capacitor. I can just add the 2 together and get the new capacitance. If you want to derive it, you can follow the steps I use for capacitors in series. The unit for the capacitance is the farad. Capital F is a symbol. The farad is a fairly large amount of capacitance. Typically, we see values of our capacitors in circuits that are microfarads or millifarads, sometimes picofarads, much, much smaller values. We are starting to see capacitances that are in the farad range. Those are the supercapacitors and ultracapacitors that I'm going to talk about in a minute. But typically in our circuits, it's usually microfarads or values in that area. Let's say I want to make this circuit on the left. 2 capacitors hooked up in series. One's twice as big as the other one. But I look in my drawer and I can't find capacitors that are those values. But I have lots of capacitors to choose from. What equivalent capacitor can I use with the same battery that will store the same amount of charge as these 2 capacitors in series? That's the equivalent capacitance. Since we're dealing with a series circuit, we use our series formula. 1 over C equivalent is 1 over C plus 1 over 2C, and I end up with 2/3 C. Take a quick look at this circuit and see if you can find its equivalent capacitance. At first glance, it looks like these capacitors might be in parallel because the way I drew them opposite each other like this. But think of the circuit as a hiking trail. If you head out from the battery, you go through the first capacitor, and then you have to go through the second capacitor. There are no forks in the road. There are no branches for you to bypass one of them. If you go through the first one, you have to go through the second one. They are in series. And we just did this one. The answer would be the same as we got last time. Now take a look at this circuit and see if you can come up with one equivalent capacitor that when hooked up to this same battery would store the same amount of charge and energy as this circuit with 3 capacitors. I try to spot combinations right away. Here I can see these 2 capacitors are in parallel. Because if I started over here at point A and I wanted to get to point B on the other side, there are 2 paths I can take, one through the first capacitor or one through the second capacitor. Those are 2 parallel paths between A and B. I can get through one capacitor without passing through the other one. These are parallel capacitors. Since these 2 capacitors are in parallel, I use my equation for parallel capacitors. C equivalent, I'll call it C equivalent 1 because I'm going to do another equivalent capacitor in a minute. This is an intermediate capacitor I'm finding as I step my way through the problem. That's going to be the capacitance of one plus the capacitance of the other one. So I can replace these 2 capacitors in parallel with a single capacitor that has a value of 2C. I'll do that now. Now I look at this circuit and I say this is like 2 capacitors in series. And I know my formula for series capacitors. So the equivalent capacitance is just C. I can replace all of these with one capacitor, value C.